Welcome back to our podcast, where we dive deep into the fascinating world of distributed systems. Today we're exploring a topic that might seem a bit mundane at first, but it's actually crucial for the functionality of these systems. Clocks. Yes, those little devices that keep our schedules in check can create some significant challenges in distributed computing. We'll break down the differences between time-of-day clocks and monotonic clocks, discuss the challenges of synchronization, and highlight some potential pitfalls that can arise when we rely on time in a distributed environment. So grab your headphones and let's jump right in. To start, let's clarify what we mean by time-of-day clocks and monotonic clocks. Time-of-day clocks, like the ones you find in your computer or smartphone, track the current date and time based on a specific calendar system, usually the Gregorian calendar. For instance, when you call clock.getTime clock realtime on a Linux machine or system.currentTime in Java, you're retrieving the number of seconds or milliseconds since the epoch, midnight UTC on January 1st, 1970. However, these clocks can be problematic. They might jump backward if the local clock is ahead of the NTP server, and they often ignore leap seconds, which makes them less reliable for measuring elapsed time. On the flip side, we have monotonic clocks. These clocks are specifically designed for measuring durations and are guaranteed to always move forward. When you use clock.getTime, clock monotonic, or system nanotime, you're working with a clock that won't jump backward, making it ideal for tracking time intervals like service response times. However, it's important to note that the absolute value of a monotonic clock is arbitrary. It's not synchronized with other systems, so you can't directly compare values across different machines. Now let's talk about synchronization. Time-of-day clocks need to be set according to an external time source, like an NTP server, to maintain accuracy. Unfortunately, this process isn't as reliable as we would hope. For example, the quartz clock in a computer can drift, running faster or slower depending on factors like the temperature of the machine. Google assumes a drift of about 200 parts per million, which can lead to significant inaccuracies over time. If a computer's clock differs too much from the NTP server, it may refuse to synchronize or reset the local clock, causing it to jump backward or forward unexpectedly. This can result in silent data loss or other subtle issues that are hard to detect. Imagine a scenario where a node in your distributed system becomes firewalled from the NTP servers. This misconfiguration might go unnoticed, and the clock could drift further away from reality, leading to potential data inconsistencies. NTP synchronization also faces limitations due to network delays. When synchronizing over the internet, a minimum error of about 35 milliseconds can be expected, with spikes that might result in errors of around a second. Sometimes, NTP servers can even be misconfigured, reporting incorrect times, which adds another layer of complexity to the situation. Leap seconds introduce yet another challenge. They can cause a minute to be either 59 or 61 seconds long, disrupting timing assumptions in systems that aren't designed to handle them. This has led to crashes in large systems, emphasizing the importance of carefully managing time in distributed environments. One potential solution is to gradually adjust for leap seconds, a technique known as smearing, but this approach isn't universally adopted. In virtual machines, things can get even trickier. The hardware clock is virtualized, and when CPU cores are shared, the clock can jump forward unexpectedly as VMs are paused. This can create additional complications for applications that rely on accurate timekeeping. Now let's consider a real-world scenario where relying on clocks can lead to dangerous outcomes. Ordering events across multiple nodes. Picture two clients writing to a distributed database. If client A writes a value and client B increments it shortly after, the timestamps generated by the time-of-day clocks could create confusion about which write is more recent. If one node's clock lags behind the other, it might incorrectly conclude that client A's write is the latest, resulting in data loss. This situation is often managed using a strategy called last write wins, where the most recent time-stamped write is retained and others are discarded. However, this method has significant flaws. It can lead to lost updates, as a node with a lagging clock may not overwrite values written by a node with a faster clock until the skew has elapsed. Additionally, it can't distinguish between sequential writes and truly concurrent writes, which can lead to violations of causality. Even with tightly synchronized clocks, network delays can cause packets to arrive with timestamps that make it seem like they were sent before they actually were. This is a classic example of how relying on time can lead to unexpected behavior in distributed systems. To mitigate these issues, it's essential to monitor clock offsets between nodes. Any node whose clock drifts too far from the others should be flagged and possibly removed from the cluster to prevent cascading problems. This proactive monitoring can help catch issues before they escalate and lead to data corruption or loss. In conclusion, while clocks may seem like the straightforward aspect of distributed systems, they introduce a host of complexities that can lead to significant challenges. Understanding the differences between time of day and monotonic clocks, the pitfalls of synchronization, and the importance of monitoring can help you design more robust systems. As we continue to rely on distributed architectures, being aware of these clock-related issues will be essential for ensuring data integrity and system reliability. Thanks for tuning in today. We hope you found this discussion enlightening. Until next time, keep your clocks in check.